Hello there, math fans. A student has asked me on the discussion board about this old exam question that has to do with projections. Just a few general notes, and then we'll talk about the problem. So the problem gives some parallelogram, asked a few questions about it. So I'm going to move this down and make a few general notes. So we do have these two projection formulas. Honestly, I don't remember them. I do remember them, but what I remember is this one formula. So if somebody said, what is projection? I would say this. It's A dot B over the magnitude of B. And I find that if I can remember this, then I can remember all of it. And I'm kind of keen on practical ways I can remember things. I know there are things I can look up if I had to. But anyways, this is the projection. This here is the thing you're projecting onto. And I find that easy to remember because it's in the denominator, and it also represents the ground. What do I mean by that? So if I draw this, and this is the ground, let's call it the ground, the thing we're projecting onto. Turns out that the length of that vector doesn't affect the projection. And then we have some other vector that we're yanking this way. We're pulling something this way, but we want to know how much of it goes the other way. And that's the main application of this, is this kind of physical application of this. And the reason we can find it, a quick reminder, is because finding this length has to do with using cosine, and then cosine comes up in our big formula for dot products, and we did that in class. That's what L is. And that's the formula. So the thing you're projecting onto, the ground, is the thing on the bottom. So I always feel like I can remember that. Okay, so let's get into the weeds of the formulas, which I don't really use myself. I just remember what I just said. But I believe the book calls this. Projection of A onto B. So if you're using that in your note sheet, then you have to remember that this is the ground. Okay, that really wasn't the student's question. The student was saying, well, there's this other formula. The other formula I never think about, because if I know the length and I know this vector, I know how to rescale. Rescaling is one of the big concepts back earlier when we were talking about vectors. So how do you rescale a vector? There was a process. You take the vector, you make it a unit vector, and then you multiply by the desired length. So if you wanted it to be length 7, you'd put a 7 here. If you wanted it to be length 10, you'd put a 10 here. If you wanted it to be length L, you'd put an L here. And that's the formula. So the formula that the book gives for the projection, and I would say that even a couple years ago when I wrote that solution, I still sometimes use the formula, but since then I've come to appreciate just the idea. So the idea is I want a vector in the direction of the ground. That's my B. I'm going to make it a unit vector. And then I'm going to multiply by the desired length. This is the desired length right here. And it's going to go there. And that is this other formula you see sometimes. And the only difference is the first one gives you a number, and the second one actually gives you the vector. But really what it's doing is rescaling. Now, if you search online for formulas for this, you will see a few different versions, because you can write it this way, and you can also write it this way. And we do this in math. We think, oh, this is a prettier way to write it. Let's write it this way. But as I said, I've come to appreciate that I can remember the first one. So the truth is I only remember this formula, and I remember that the denominator is the ground. And then if I ever need the vector projection, I rescale the ground vector to the desired length. Okay, so there's projection. Now let's get to the problem. So again, for me, this is the only thing I remember. I don't even use these at all anymore. All right, I find the length, and then if I need to rescale, I do it. It is true that the thing in the denominator is always the ground. Okay, so let's get to the problem itself. The parallelogram below has these points, A, B, C. It has this little point over here. That's the part that I might have to do with projection. The first problem says find the point C. Now, this wasn't what the student was asking, but I thought I would say something about this. Because ultimately, if you know it's a parallelogram, and you know this point is 1, 2, 3, and you know the vector. So this is a common thing I see students get confused on. If I hand you a vector and I tell you the vector is 3, -1, 0, and I tell you that the tail of the vector is at 1, 2, 3, then you automatically know this point. The truth is, if you know any two of those things, you know the other thing. Why is that? Because a vector represents the changes. It says to get from here to here, you have to go up 3, down 1, not change. So up 3 from 1 would be 4. Down 1 from 2 would be 1, and if you don't change, it's 3. So that was the point of this question. Often people get confused because you're mixing concepts of vectors with points. But if you can remember that a vector is the change when you go from A to D, and that this is the start and this is the end, and they gave me the start, then automatically that tells me what the point D is. Now you say, hold on, that's not the question. The question was not to find the point D. But I just wanted to talk about that first. So the point D would be 4, 1, 3. So I get this, 4, 1, 3. And they also told me this was 2, 3, 5. Now how you get to see there's several different ways. You could realize it's a parallelogram. So this vector is the same as this vector. That's probably the easiest way. So we actually know B, C, I don't know if it's the easiest way, is the same as this other vector. They're the same vectors. So you can do the same thing. If you want to get to point C, you go from the point B, you add 3, so this is going to be 5. You subtract 1, this is going to be 2. You add 0, this is going to be 5. Yay. Okay, so that was a small question. I can't remember if that was like a point or something. It was kind of seeing if a student could reason out what the vector told us was this other point. There were other ways to get there too. Okay, so then there was a question about the point E. In particular, it asked us to find the BE vector. It's another one of these that's kind of open-ended in that there's probably a lot of ways you could get there. One strategy is you could find the point E and then do E minus D to get the vector. That would be one strategy, meaning do this by subtraction. Do something. Subtract the point D. This wouldn't be great if you didn't have the point D yet. But the challenge then would be to find the point E. So that's kind of hitting a snag. So what else could we say? Well, there might be a projection going on there. If we want to think of it as a projection, we're going to need to make sure we decide what the ground is, what vector we're using, and that the two things are tail to tail. So how could I possibly do this? And I think there's many correct approaches. We're projecting onto AB or BA because that's where it's perpendicular. I know it's turned in a funny way, but you see where the perpendicular piece is. That's where the ground is. This is the ground of my projection. Ground. The thing I'm projecting down onto. So it's just that it's kind of turned in a way. I think maybe that could bother someone. But if I turn things slightly, maybe this would help. Let's say it looked like this. Same parallelogram. I have AB, I have D, I have C. I'm going straight down. This is E. So when I look at that, what it looks like to me is I'm projecting AD onto AB. I'm coming straight down. I know it's pointed that way instead, but it's still the same thing. So they're tail to tail. I have AD, I have AB. So what I see is I want to do, here's how I would think through the problem if I was doing it myself, didn't have a formula sheet in front of me. I would say I want to project AD onto the ground, which is AB. And I would deduce everything else I needed from this. Notice that I realized what the ground was. And now I'm off. So the question is, do I have those? And this is what's nice. If you do realize you have a projection problem, then this usually leads to a fast answer. Now, AB I don't have. I think you got it earlier in an earlier part of that particular question, but I'll write it up here. AB squared to B minus A is 1, 1, 2. So this is 1, 1, 2. And I'm projecting onto AB, so this is going to be the square root of 1 plus 1 plus 4 square root of 6. So this length, that projection length, is 3 minus 1 plus 0 over the square root of 6. So this little length here, from A to E, I now know, is 2 over the square root of 6. There's lots of ways I could write that. 2 over the square root of 6. Okay, so at that moment, there's probably a lot of ways to go to finish this problem off. You could try to find the point E and go back to this strategy, because now we know how far along we have to go. So let me think about that for a second if I wanted to do that. I could say, I want to go in the direction of AB, but I only want something to be this long. Okay, so I could find the AE vector. This is not what I did in my solutions, but you could do this. How would you find it? It would be the projection vector. You would say, I need it to be 2 over root 6 is the length, the desired length. And I need to rescale the ground vector AB, which is 1, 1, 2. And that makes it a unit vector. And we've done it. So this is the vector AE, 2, 6. So it's going to be 1/3, 1, 1, 2. Now, the challenge of this question is there wasn't like a clear one direct path. That's what made it hard. But now I have the vector AE. If I was stuck at this point, I could say, well, I could get the point E if I wanted. How would I get the point E? Well, I know the point A. I have the vector AE, so I can add. I can say I need to go up 1/3, up 1/3, up 2/3. So that means that E has to be, what would it be? It started at 1, it has to go up 1/3. Let's just write it this way, 1 plus 1/3. This has to be 2 plus 1/3. This has to be 3 plus 2/3. So that's one way to answer the question, is now that we have the point E, we could plug it in here, subtract, and we'd have DE. Another way to do the question is, if you have 2 points in general or 2 vectors, you can subtract to get the vector that goes between them. Let's run a few scenarios here if we're confused by what I just said. So let's do this. Let's take like examples that we can use. And this is something you could do if you really were struggling on a test. Let's just take examples that are on the axes. So how about this? 0, 3, 2, 0. And let's call this A, and let's call this B. Don't know why I'm using all the colors. If you subtract the 2 vectors, let's say you do A minus B, what do you get? So A minus B, so you're going to have 2 minus 0, so it's going to be 2. 0 minus 3, so it's going to be negative 3. If you draw that, it looks like this. It goes over 2, down 3. It's that. We think more in terms of vector sums usually, but the difference is that directed line summing. It doesn't matter if they're vectors or points. It gives you the vector that goes from there to there. I suspect that's what the question was about, is because that's what I did in my solutions, is I said, I have these two vectors, so I'm just going to subtract. I'm going to do that point. Which one did we want? DE. I'm going to do this point minus that point. So in general, if you want the vector that goes from D to E, you want to do E minus D, the points. That's not a notation. You can do that with vectors that point at them or points themselves. So I think I did AE minus AD in my solutions. That's accomplishing the same thing. So it's a few different ways to say the same thing. I'm trying to say it in lots of different ways to see if that helps. So let's refocus here. The moment I saw it was a projection, I computed this number, 2 over the square root of 6. I then realized it had to do with a vector. So then I found the vector that actually points that way and has that length. And that was my AE vector. And that was 1/3, 1/3. This was a challenge question, 2/3. I already had the vector AD, which was 3, -1, 0. And I wanted to get the vector DE. Now that's the vector that goes from D to E. So I think the main question was this fact of, you can do, if you had the point E and had the point D, you would just subtract. But you can also do it with the vectors. So you can do AE minus AD. It gives you the same changes. So that's what I did in my solutions, is I did the 1/3 minus 3, 1/3 minus -1, 2/3 minus 0. And that it came out to be whatever it was. Let's see. That's going to be 9/3, so it's going to be -8/3. This is going to be 3/3, so it's going to be 4/3, 2/3. I probably should check the solutions here because I know that I'm just going to pull up while I'm thinking here. There's a post about this. Okay, that matches. All right, hope that answers your questions. Mostly, I hope that gives you another deeper discussion of projections. All right.